nanotubes on thermal properties and crystalline structure of e-waste ABS. To help you better follow my presentation, I propose the following outline. I will start with the introduction, the rise of e-waste, a global challenge. What about e-waste ABS? Current recycling method for plastics, statement of the problem, the methodological approach, and the objectives. In the experimental part, I will present the materials used, the technique for elaboration of the samples, and their characterizations. I will present the main result obtained by FTIR, X-ray diffraction, TGA, and T-cell test. I will finish with a conclusion. E-waste is the waste from electrical and electronic devices that use electricity to work. The rise of e-waste posing a significant problem. The projection of e-waste production worldwide from 2019 to 2030 increased by 48%, which is important. This is a significant increase with many consequences. The first one is the health risks. Exposure to toxic substance found in e-waste can cause various health problems. The second consequence is the pollution. E-waste contains hazardous materials that can contaminate soil, water, and air, like shown in figure 2. E-waste has useful material and harmful substance. This includes metal, glass, plastics, and circuit boards. ABS is a common plastic found, around 38%, in a wide variety of electronic devices, such as smartphones, laptops, and television. It's a copolymer composed of acrylonitrile-Butadiene and styrene, and offers good properties such as high impact resistance, durability, and moldability. It can be found in many applications such as electronic casting, automotive parts, and toys. ABS has good properties, making it an excellent engineering material, and it's relatively expensive material compared to other plastics used in electronics. Next to that, there is a reduction of environmental impact, conservation of natural resources, and contribution to the circular economy. That's why it's important to recycle e-waste ABS. While recycling e-waste ABS is challenging, several methods are being developed and implemented. This method aims to maximize material recovery and minimize environmental impact. There are mechanical recycling, chemical recycling, which involve breaking down plastic into its monomers, and advanced recycling like enzymatic depolymerization. The thermomechanical recycling is the most widely used method for processing e-waste ABS, but it's difficult because of the oxidative degradation of the polybutadiene rubber phase during service time. An interesting approach to recycle e-waste ABS is to use Halloysite nanotubes as filler to improve mechanical properties, thermal stability, and flame retendency. Several studies have demonstrated the effectiveness of HNT, which is naturally occurring clay minerals composed of hydride aluminum silicate, and they have a tubular structure, exhibit a range of desirable properties, including high aspiration and biocompatibility, and it's used in various sectors. So the objective of this study is to analyze the impact of HNT on the structure of e-waste ABS and evaluate the modification of mechanical and thermal properties to assess the effectiveness of HNT in recycling e-waste ABS. In the experimental part, the first step involves collecting e-waste ABS. The recovery process includes the following stage: the collecting of cutting of computer screen and launching phone, Manual sorting and only ABS waste with a marking ABS is considered. Decontamination, cleaning, and washing. And then e-waste ABS cut into small pieces and crushed using a polylabra bender. And in final, we have flags of almost 1 centimeter size. So we use virgin ABS, which is supplied by SABIC under the grad Sicolac. We use e-waste ABS and the Algerian Halloysite from Jebel Debar in Algeria, which has been ground into powder, as we can see in Figure 5. Prior to processing, virgin ABS and e-waste ABS and HNT were dried for 24 hours at 80 degrees Celsius to remove all humidity present in the samples. The processing was carried out using an internal mixer and molding using a thermocompression. And then we have sample show in Figure 6. We use different characterization techniques, which are tear, X-ray diffraction, TGA, and tensile test. The first technique used is infrared, which is a method for analyzing chemical composition and molecular structure. The Figure 6 shows the infrared spectrum of virgin ABS, e-waste ABS, and e-waste ABS reinforced with 5 weight percent of HNT. The spectra of virgin ABS and e-waste ABS show the characteristic peaks of ABS, which include the aliphatic and aromatic bond, aliphatic and aromatic CH, the acrylonitrile peak at 2237, and the C double bond C from polybutadiene. However, there are some differences. The virgin ABS exhibit peak at 1737, indicate a carbonyl stretching of ester groups. According to the literature, it can be the stabilizer like HALS or phenolic antioxidants. The appearance of 2 other peaks, the first one at 737 corresponding to the antimony, and the second at 871 indicate the C-Cl bond vibration, confirming the presence of chlorine-containing elements. We have 3 other bands at 3,300, 1,636, and 1,557, which can be attributed to the NO stretching in nitro component, suggesting the presence of hardeners or antistatic additives. The e-waste ABS reinforced with HNT show a peak at 3,685 for OH, another peak for SEO, and the third peak for SEO-SE, which indicate the presence of HNT. In summary, FTIR data show a similar chemical structure between virgin and e-waste ABS, except that for the later, the presence of additives such as flame retardants. The addition of HNT in e-waste ABS is also confirmed through the presence of the band characteristic of HNT. The second technique is X-ray diffraction, which helps us study the crystal structure and the composition of the samples. The Figure 11 shows the X-ray spectrum of virgin ABS. We can see a broad and significant band observed between 10 and 25 degrees, characteristic of the amorphous structure of ABS. Sorry. Okay. The second technique is X-ray. Sorry. The second spectrum is the spectrum of waste ABS. show several sharp peaks corresponding to the crystalline structure of titanium dioxide and antimony trioxide, which are used as a white pigment and flame retardant, respectively. The X-ray spectrum of the nanocomposite shows the appearance of characteristic peaks of HNT at 2 theta equal 12.36 and 2 theta equal 24.86, corresponding to the dehydrated halloysite. Thank you, sorry. In summary, X-ray diffraction shows the presence of additive, mainly flame retardants and pigments in E-waste ABS. Further, HNT is also detected in X-ray diffraction spectrum of E-waste, but it has negligible effect on the crystalline structure. The third technique is thermogravimetric analysis, which helps us examine the thermostability of the samples. The figure 8 shows that the TGA and DTG curves of virgin ABS, E-waste ABS, and E-waste ABS with HNT. The virgin ABS show a single degradation step with a residue rate with almost 0%. This indicates a complete degradation at 900 degrees Celsius. E-waste ABS exhibits 3 degradation steps, which can be explained by the presence of some additives. And E-waste ABS is less thermally stable than virgin ABS because of its degradation by chain scission. The nanocomposite exhibits better thermal stability than the neat E-waste ABS, because the tubular structure of halloysite acts as a physical barrier, limiting the diffusion of volatile degradation product and slowing thermal degradation. In summary, E-waste ABS is less stable than virgin ABS due to degradation by chain scission. HNT has improved the thermal stability of E-waste ABS through its barrier effect and the formation of shell layer. The last technique is tensile testing, which will inform us about the mechanical behavior of ABS. Virgin ABS exhibits mechanical behavior similar to that of thermoplastics, characterized by good softness and rigidity. The mechanical behavior of E-waste ABS is different to that of virgin ABS and exhibits reduced tensile strength and decreased ductility due to the presence of the additives. The nanocomposite show better mechanical behavior than E-waste ABS because the tubular structure of E-waste helps to eventually distribute load across the material, which lowers stress concentration. So virgin ABS has good mechanical properties. E-waste ABS exhibits the mechanical behavior of brittle materials, and the HNT improves the mechanical properties of E-waste by acting as a reinforcing agent that enhances strength and stiffness. In conclusion, the addition of HNT into E-waste ABS after one reprocessing cycle shows an improvement in thermal and tensile properties, while no effect is observed on the intrinsic chemical structure of E-waste ABS. Further, the study also highlights the potential of HNT in enhancing recycled E-waste ABS. This contributes to better material performance and sustainability. I will thank the International Atomic Energy Agency for their support. Thank you for your attention.